Okay, we know that when electrons are fired at a metal foil, that the electrons can diffract between the atoms in the foil and form an interference pattern on the screen like this. So the electrons are acting as waves. How do we calculate the wavelength of this wave? Okay, de Broglie said that the particles have wave-like properties, and the wavelength of the particles is given by this equation where lambda is the wavelength in meters, h is the Planck's constant, and p here is the momentum. Okay, momentum is mass times velocity or mass times speed. Okay, so we can use this equation to calculate the wavelength. We calculate the wavelength of an electron moving at 5.0 times 10 to the 6 meters per second. So I'm going to write de Broglie's wavelength equation, okay, using Planck's constant, and then divide it by the mass of the electron times by the speed. And that gives me 1.5 10 to the power of minus 10 meters, which is less than a nanometer. Explain why electron diffraction cannot be observed using Young's double slit. So Young's double slit is used for diffraction of visible light and to form an interference pattern with light. Light has a wavelength around 350 to 700 nanometers. So the slit separation and gap sizes are approximately that size. And this wavelength of this electron here is less than a nanometer. So unfortunately these gap sizes won't be small enough. So you'll need a smaller gap size, and that's typically the gaps between atoms in a crystal or in a metal foil. So in this diagram we have two metal plates. It's connected by some battery there, which is applying a potential difference, and there's an electron on the one end, and this is going to be accelerated, attracted towards the positive plate, and it's going to cause it to speed up. And we want to find the wavelength from using the potential difference, the mass, and the charge. So firstly, the de Broglie wavelength, so we'll write that equation down. And then we need to understand what potential difference is. Potential difference is work done per unit charge, which just means energy per unit charge. I'm going to use lowercase q, but you can also use E because it's an electron that, or if you're using an electron. Okay, so I'm going to rearrange this to make energy the subject. So the particle here, the electric potential energy, which is over here, turns into kinetic energy. So instead of using electric potential energy, I can just use kinetic energy because it's gaining speed and it's gaining kinetic energy. So I'm going to use half mv squared there. And what I'm going to do now is I'm going to multiply both sides by m. The reason for this, which will come clear in a minute, is because I want to get rid of momentum. But in this equation, there's one m and two v's there. So I'm going to multiply both sides by m. That gives me m qv, and then I got half m squared v squared. Okay, so now I'm going to bring the 2 to the other side and then square root it. So this is why I did that, so I can get that momentum mv. Now I can just replace the momentum in this equation here, and this is the equation that we're looking for. Okay, describe and explain how increasing the voltage used will change the pattern on the screen. Okay, so first I'm going to use this equation we just derived. By increasing the voltage, I'm increasing the bottom of that equation there, which is the momentum. So the momentum is higher, the wavelength decreases. So in this, I've just assumed that the mass of the particles is constant, the charge constant, and the gap size of the crystal is constant, and increasing the potential difference increases the momentum, which causes the wavelength decrease. To see what happens when the wavelength decreases to the pattern formed on the screen, we'll use the diffraction grating equation from the waves topic. So any given order, I'm going to take the, let's say the first order, so ignoring n there, and obviously the slit separation, which is the distance between the slits here, that's constant. Okay, so if we decrease the wavelength, sine theta decreases, which means that theta also decreases. Okay, so the angle of a given order will be smaller. Okay, so the rings will appear closer together, and maybe the diameter will be smaller, and there will be more rings on the screen as well.